Here. Okay, so first off, the position time graph. Let's have Isaiah, will you talk about how you use your position time graph to come up with your written description?
Whoa.
Oh, yeah, we don't have
Lice. Okay, so
that's cool.
Because it's staying in the same place over this period of time, staying in place over that period of time to get that graph.
So position is what, Isaiah?
Position is the same. I don't know.
Yeah. Well, what is in general? What is position?
It's location.
Okay, and so that location is not changing, right?
Yeah.
And so that's not why you wrote that. You're just gonna stand there, right?
Yeah.
Okay. So now you guys, your motion map. Talk to me about your motion map.
There was no movement.
You're right.
The motion map to have any evidence of any motion in motion. So that's why we didn't put anything up.
Okay, so you have tick marks, which represent position, which is good.
Yeah.
What do the dots represent? Look around behind you. What do the dots represent?
The position, like where it was at a certain point in time.
Okay, so the location or position at a given clock reading. Is the clock ticking on this to create that position time graph?
It should.
Yeah. I mean, you're seeing on position time graph that it's moving. It's making a line, therefore time is progressing.
Yeah.
So how is the position changing as time progresses?
It doesn't change.
Right. So the dots should still be there because it's at a given clock
Would it be
reading.
like on a, or would it be?
Yeah. Will you fix it?
I don't know what you mean. Like, would it be going that way or would it be going that way?
Which one do you think represent? Because the tick marks represent position, right?
Yeah.
And so which one would make more sense?
Up.
Up, because it's not changing
it.
it.
Zero.
Say what?
Would it stay on zero?
Would what stay on zero? The dots?
dots.
Well, let's see. Back over there, Isaiah. Where on your graph, on the position time graph, is the motion detector? Where's the location of the motion detector? Anybody can answer this. Where is the Yeah, position of 0. Point to that. Where's position of 0 on your position time graph, Isaiah? So where's position time graph? Where's 0? Right there, right? It's above 0, right?
Yeah.
So therefore it should be, like Isaiah has drawn, above 0. To the right of 0. That make sense?
Yes. Yes. I'm sorry.
It doesn't?
No.
Okay, so where do you understand why you need to include dots?
Yeah, I understand that. It's just if that's time, then how?
Oh, that's not time though. That's position. The ticks represent position. And so the dots represent position at a given clock reading.
Not on zero.
And so go ahead.
I think what he's saying is position on the graph is not at zero.
You're right. The position on the position time graph is not at 0.
So it wouldn't be on zero.
Right. Yeah, so on
It would be ahead of zero.
It just sits there.
yeah, and now both you guys, I have a question for you on the motion maps. What do arrows represent, Isaiah? Continue or stop.
On the motion?
Yeah, on the motion maps.
I don't really know. I just kind of put it there.
Someone.
I see the pattern. I'm seeing the pattern.
Yeah, arrows represent velocity, and velocity is the slope of a position time graph. So, yeah, there you go. Yeah, it's just dots on top of each other. That makes sense? More clear now?
Yes, sir.
Okay, now the velocity time graph. Both of you drew flat lines. Although, Isaiah, talk to me about your velocity time graph. Why is it drawn like that? Where is it drawn at? What value is the velocity?
0 velocity.
Why?
Because there's no velocity.
No velocity, I can tell that 2 ways. 1, there's no slope. 2, on a motion map, how can I tell there's no velocity?
There's no movement left or right, it's just straight.
And there's no arrows, right? No arrows means flat line on velocity at 0. Any questions on 1? Good, you guys can sit down. Number 2, you guys are up.
3 races.
Just leave it to the side for now. Cassie and Cole, talk to me about your position time graph and how you came up with your written description.
Oh, what's that?
Yeah.
Um,
Hey, oh, and by the way, you guys should be checking this in your own notebook because I'm going to expect the correct answers written in your composition books. So as they're going along, even if you don't have it done, you should be working along with them. Understand?
Yes.
Okay. Go ahead.
okay, so our starting point was 0.25 meters, which we had that calculated on, like, with the sensor and stuff, and on Plotly to give us that. Our direction moved, we moved away from the sensor with that. Path movement was slow walking, and then relative speed, I realized that is wrong. It is slow.
That's okay. Just out of curiosity, how did you get the relative speed?
Slow.
Slow. Okay, cool. You guys, hey, this is a really good written description. It looks like they did the same thing. They highlighted 3 really important things. First off, the starting position. Second off, the direction moved. Third off, how fast they're walking, whether they're walking slow or fast or whatever. Right? That's good. That's really good written description. Now, you guys, talk to me about your motion map.
Okay, well, we started over here because we started away from the motion detector. And then since it's just a constant slope, all of the lines were the same, so we put tick marks on them.
Oh, we should have done that too.
What did you say, Cassie?
We should have done the tick marks too,
Now, why should you have put the tick marks?
because they're constant.
Okay, and how do you know that just by looking at the position time graph?
Just because like it has like a constant slope.
Slope is not changing. Good. Okay. Any questions on their motion map? That's a really good motion map as well. Velocity time. Cassie and Cole, you guys want to talk about your velocity time?
Our velocity, like since it was going at the same speed pretty much the whole time, it was same speed across like our original.
Okay, and why is it a positive number, Jess or Clara?
We went towards it.
Say what?
We went towards it, we didn't go backwards.
Because it's above 0. If it was below this axis, then it would be a negative number because it would be a negative velocity. But
So what you're saying is if you took that line of the position time graph and shifted it below 0, that would have been a negative. That would have been.
no, if it was going down, it would be
Okay, good. Why is going down, Jess? Why would that make it negative as opposed and going up making it positive?
Away.
Say what?
We're going away from it.
Sure. Yeah. And what's the definition of of velocity? What is the definition of velocity? The slope of what line?
the slope of the position time graph.
And the slope in this case is positive or negative?
Positive.
Positive, and it's not changing. Therefore, the velocity should be positive. Now, there's one other way I can tell the velocity. So, both of your velocity time graphs look really good. It's a positive number, flat. But there's another way I should be able to tell if the velocity is constant and it's positive.
These arrows.
Okay, so notice on the motion maps that we can call to the right, anything going to the right, positive, anything going to the left, negative velocity. And the equality marks indicate that it's a constant value. Make sense? Cool, number 3, go.
You want us to erase the boards?
Just leave them for now. Leave them for now. Make sure you're correcting yours as we go along.
How did we do?
Number 3. Now, you guys drew the one that you made in the lab, is that right? Is that why it's all curvy?
On the velocity, yeah.
And the position time? Because I think, like it was straight, wasn't like a, yeah, it's supposed to look like that, but I think that's what you created in the lab, I think. Okay, that's fine. Okay, cool. So, you guys talk to me how you created that graph then.
Which one?
The position time. Talk to me how you did the written description.
Okay, well we just walk towards the motion detector without stopping, like at a constant speed.
Okay, and so where'd you start?
We started away from
Okay, so you started away from the motion detector and you move towards it, right? At a constant rate, right? Okay, now, does you guys just look like it's a constant rate, your position time graph? Why, Emily? Why does the velocity?
Same speed.
Say what? What am I looking for if it's a constant rate or a constant velocity? A straight what?
linear line.
Straight line, right? That's not straight, right? Your slope is clearly changing as that goes. John?
I could also say we had a problem on our first one that our position of time graph was weird because whenever you do it, it shrinks the graph.
Yeah, you have.
So if
Yeah.
you made it bigger, it actually probably would look straight.
Yeah, that's a good point. Whenever you use those motion detectors, they like automatically adjust the y-axis and x-axis. So you want to adjust it to where it looks better. Okay, motion map. Talk to me guys.
Okay, so basically it was going down, so it had a negative velocity, and so to show negative velocity, you go backwards. And so this is starting at the position. Except we had a question on this because is this the right way to do it, or would
Or would what?
I'm talking about this? Would we put the 0 right here, or would it go somewhere else?
So what's that 0 indicate?
That's where it started, I guess.
That's where the what is it called, motion detector is?
Yeah. The ticks represent motion. Hey, Cassie and Colton, you guys see?
So
If you need to move, move.
okay,
Sorry,
so the 0 should have been over here.
Well, so is that where the motion detector is?
Oh well. Okay. Okay, so this is right.
Yeah, so you're moving towards the motion detector. The one thing that neither one of you guys did indicate is where are you starting?
Like a number.
Yeah, well, where's my starting position?
The T
It's
equals
kind of
0.
Yeah.
arrows, isn't it?
Yeah, it kind of is, but sometimes it gets confusing if I'm going multiple directions and things. What'd you say, Thomas?
The T equals 0 should be underneath our start.
Yeah, the T equals 0 should be underneath that first dot that you put there. Okay? Other than that, the motion maps look good. Okay? Velocity time. You guys want to talk about that?
Ours kind of like it has the curve at the bottom because whenever I was walking backwards, I kind of slowed down because I knew I was going to walk forward again. So.
Okay, usually I try and stay in the back during whiteboard sessions, but because it's going to be very difficult for me to communicate what I'm talking about, I'm coming up here. If we look at this part right here. By the way, the reason they're stacked is so that we can easily compare position time and velocity time. If we look at just this portion up here, how's that compared to theirs over there?
Equal.
It's pretty similar, right? There's a little bit of curvature here. If we compare this to what they have, you see how this is somewhat flat? Okay, so obviously what they did over there was correct. So Bobby and Taylor, talk to me why you created your velocity time graph that way.
Well, since on this graph it's going down and it has a negative slope, that means it has to have a negative velocity because
And it has to be constant.
negative
so-
4x, negative 4.
Yeah, good. Yeah, did you guys see why it should be constant and negative, everyone? Slope is not changing and it's a negative slope, therefore the velocity is not going to change at a certain negative value. Any questions on 3? 4, you're up. We only got one 4Z, right?
Yeah.
Make sure, once again, you guys are making these changes in your comp books.
Did we like feedback on Brown?
No, leave them blank or leave them as is for now.
I think I messed up on the velocity. So
That's okay. Okay, the position time graph is like as such. Now, is that flat? The second part of that was okay. So that's flat. Okay.
Yeah.
Cool. All right. So tell me about your written description then, Colton or John.
Basically what we did is we just walked towards it, and then stopped.